All right, so now we are going to prove the theorem, the mean value theorem for harmonic functions. So the theorem is as follows. So you work with on a domain to consider the Laplace equation on the domain omega, which is a subset of R to the n. So we assume that here, so Laplacian of u equals 0 on omega, and we consider a ball B of radius r centered at y with y in omega. And so you assume that for this r, you are strictly included in omega. Then you have that the value of u at the point y equals what? Equals an integral of u across the sphere of radius r, so it's the border of the ball of radius r, times a constant which is 1 divided by n times r to the n minus 1, and here omega n is the volume of the unit sphere. So omega n is the integral across the ball of radius r of gx. And you have also that u of y is 1 divided by omega n times r to the n times the integral. And here the difference is I integrate all across the ball, whereas here I was integrating only on the border. Okay. All right. So the point of this session is to prove this theorem. So proof. First of all, we are considering a row belonging to 0r. Just a quick remark on the references. So here I'm following the proof appearing on the book of Gilbert Schrödinger, classical one on analytic equations. You can find the proof. The proof is the same, but it's written not on the same order. On Evans, the book of Evans about partial differential equations, and also the book of Just, also on partial differential equations. So that being said, I start to write that, so 0 equals, I know that the Laplacian of u is 0, and if I take the integral all across the ball of radius r, it's still 0. And here I apply the divergence theorem here. So I obtain the integral on the border of the gradient of u, and I do the product scalar with the scalar product with n is the normal unit vector, and here I integrate on the border, so on the sphere. Okay. Just maybe we can spend some time to recall what the divergence theorem is. And so what's the divergence? So the divergence of f, if f is a function from R to the N into R to the N, which at x1, xn associates f1 of x, f2 of x, fn of x. So the divergence of f is the sum from I equals 1 to n of the partial derivative of f with respect to xi at x. All right, and the divergence theorem says that the integral over omega of the divergence of f, so gx, this is the Lebesgue measure, equals the integral on the border of omega of f times n. Here, this is the measure on the border. And okay, I want to emphasize that just this is a generalization to the dimension n of the fact that the integral between a and b of f prime of x dx equals f of b minus f of a. So you can consider that here f de b times 1 is exactly this at b, and f of a times 1 is this at a. And so you can prove that this formula holds. Okay, so let's get back to our proof. So I applied here the divergence theorem. So now I have that 0 equals the integral over the border of the gradient of u scalar my normal unit vector. Yes. Okay. First thing. Next thing is that I'm going to do a change of variables. All right, so I will just write that so my x here is over this sphere. So I can just write here, it's the gradient of r time y plus, let's say that this is rho, and this will be x minus y divided by x minus y. And I keep the rest. With rho equals actually the norm of x minus y, and x belongs to this sphere of radius r. Right. But so sorry, I will just write this on a general. It's a rho, right? I'm not integrating on. It's a rho that belongs to 0 r. All right. From there, instead of integrating on the sphere of radius r, I'm going to integrate on the sphere of radius 1. And so I will write that here. I will write this as omega. Right. So when I do that, so I can write that. But now my ds, let's write it d sigma. Now my measure is not on the sphere of radius rho, but on the sphere of radius 1. So here I have a factor rho to the power n minus 1. That's classical thing for the balls. You have this factor appearing here. And here I will just make some change. I can remark that here now my exterior unit normal vector is actually its omega. Okay, but now I can remark, so I don't change the interval, but I can remark that actually this thing is just the derivative with respect to rho of u y plus rho omega u sigma. Okay, so now I'm almost done. What I'm going to do, I'm just again coming back to my integral over not the sphere of unit 1, but the sphere of radius rho. And what I get is that this is equal to of rho n minus 1, and this here so first, oops, first, first I can take, so if everything is regular, I can take the derivative out. So I took the derivative out of the integral sign. All right, and now I'm going to come back to my wall of radius rho. So I will get here a factor while minus n, and here it's just writing q. And it's the border. Okay, but this is 0, right? This is 0. So uh, this means that if the derivative of this thing is 0, it means that this is a constant. So if this is a constant, I have that for any rho, equals the value at r. So I can write it like that. And this is the end of the second step. So the last step So this is good. This is good because this expression and that appear in my expression in the theorem. So to end the proof, I'm going to compute the limit as rho is going to 0 of this quantity. Okay, so let's compute the limits as rho goes to 0 of rho 1 minus n of the integral u. Yes. So the other thing that appears in the theorem, it's the area of the unit sphere. So I'm going back to the unit sphere, and I know that I have a factor of rho n minus 1, but here I change, and now I'm integrating over the ball of radius 1. And so as rho is going to 0, this is exactly u of y times gamma n moins 1, where n minus 1, where gamma n minus 1 is where gamma n minus 1 equals the integral over the sphere of radius 1 of ds. But it is known that this is n, and yeah, I call it omega n, where omega n equals not the integral over the sphere, but all over the ball. And so I have this formula. So the first part of the theorem is proved now because this is equal to r and r times 1 minus n. This is equal to r 1 minus n, the integral of u. Yes. So putting this thing on this side, I got that u y equals 1 divided by omega n r n minus 1, the integral over the border of u y. Yes. And this was the first part of the theorem. To complete the proof, I'm just writing that omega n r n minus 1 u y equals the integral over the sphere of u y ds, and I will integrate that between 0 and r with respect to r. So if I integrate that with respect to r, I got exactly the integral all over the ball. And here, so I will get r to the n, I will get r on rn omega n u y. So finally, what I obtain is that finally u y equals 1 divided by r to the n omega n, the integral over the ball of u x dx. All right, so now the theorem. It's proved.